Welcome to Calculus. Today we are going to explore a fascinating and highly intuitive concept known as Rolle's theorem. Imagine you are hiking up a mountain and then walking back down to your exact starting elevation. Common sense tells us that to go up and come back down, there must have been a specific moment at the very top where you stopped going up and were about to go down. At that exact peak, your path was perfectly flat. This simple, everyday idea is exactly what Rolle's theorem proves mathematically. Let us dive in and see how it works. Now that we understand the hiking analogy, let us translate this into formal mathematical language. For Rolle's theorem to apply, a function must meet three strict conditions. First, the function must be continuous on a closed interval from a to b. This means you can draw the graph without ever lifting your pen. Second, it must be differentiable on the open interval from a to b, meaning the curve is perfectly smooth with no sharp corners or vertical jumps. Finally, the starting height must exactly equal the ending height, which we write as f of a equals f of b. If even one of these fails, the theorem cannot be used. Once we have verified those three conditions, what exactly does the theorem give us? It guarantees that there must exist at least one point, which we call C, somewhere strictly between A and B, where the derivative is exactly zero. In this formula, f prime of C represents the exact slope of the tangent line at that specific point. The value 0 means the slope is completely flat or horizontal. The point C is simply the horizontal coordinate where this flat spot occurs. If the curve wiggles up and down, there might be several such points, but the theorem guarantees there is always at least one. Before we move on, let us see this with a concrete visual example. The diagram on screen perfectly visualizes the theorem in action. You can see the blue curve starting at point A and ending at point B on the exact same horizontal line. Because the curve is smooth and unbroken, it must turn around to get back to that starting height. Right at the turning point, labeled as C on the horizontal axis, the tangent line is perfectly horizontal. This visual proof shows exactly why the derivative, which measures the steepness of that tangent line, must be zero at that specific location. Now that we have seen the formula and the graph, let us apply Rolle's theorem to a real mathematical problem. We are given a simple parabola defined by the function x squared minus 4x plus 3 on the closed interval from 1 to 3. First, we check our conditions. Since this is a polynomial, it is naturally continuous and smooth everywhere, satisfying the first two conditions. Next, we must calculate the height at our starting point, x equals 1. By substituting 1 into the equation, we find that the starting height is exactly 0. It rests perfectly on the horizontal axis. Continuing with our endpoint checks, we must perform the exact same substitution for the ending point of our interval, which is 3. Plugging 3 into the equation yields 9 minus 12 plus 3, which also perfectly equals to 0. Because the starting height and ending height are identical, the third and final condition of Rolle's theorem is completely satisfied. The theorem now absolutely guarantees a flat spot exists. To find its exact location, we use the power rule to find the general derivative of a function, which gives us 2x minus 4. Now we simply need to find where this slope is perfectly flat. We replace the general variable x with our specific target point c and set the derivative equal to 0. This gives us the basic algebraic equation 2c minus 4 equals 0. Adding 4 to both sides and dividing by 2, we isolate c. Finally, we verify that our result is strictly between our interval endpoints of 1 and 3. It is. Physically, this means the exact bottom of the parabola, where the tangent line is perfectly horizontal, occurs exactly at x equals 2. Let us look at a slightly different scenario, using a wave-like function. We will examine the sine function on the closed interval from 0 to pi. The sine wave is a fundamental, smooth curve with no breaks, so continuity and differentiability are easily satisfied. Next, we check the endpoints. At the starting point 0, the sine function evaluates exactly to 0. At the ending point pi, it once again evaluates exactly to 0. Because the starting and ending heights are identical, all three strict conditions are successfully met. We are mathematically guaranteed to find a smooth peak. To locate this peak, we start by taking the derivative of the sine function, which is the cosine function. To find where the sine wave flattens out, we set this derivative equal to 0, giving us cosine of c equals 0. We now need to find the specific angle between 0 and pi where the cosine equals 0. In trigonometry, this happens exactly halfway through our interval. Visually, this means the sine wave starts at 0, rises to a smooth peak exactly at pi over 2, and then falls back down to 0. So, we have successfully used the formula in 2 examples. This brings us to the proof. To truly understand a theorem, we must prove why it is absolutely true every single time. The proof relies on the extreme value theorem, which states that any continuous function on a closed interval must reach a maximum and a minimum. This leaves us with 2 scenarios. The first scenario is that the function is completely flat everywhere, like a straight horizontal line. In this case, the slope is 0 at every single point. The theorem is instantly proven for this simple case. Now, let us look at the second, much more common scenario. The function is not a flat line, meaning it actually goes up or down. Since the starting height and ending height are exactly the same, the function must reach its maximum or minimum at some interior point strictly between A and B. Let us call this point C. By Fermat's interior extremum theorem, if a differentiable function reaches a peak or valley at an interior point, the derivative there must be exactly 0. We have now proven that whether the function is flat or wavy, there will always be a flat spot. So, we have proven that the theorem holds. This brings us to an important question. Why do mathematicians care so much about proving that a flat spot exists? Rolle's theorem is incredibly important because it acts as the foundational building block for almost all advanced calculus. Without it, we could not prove the mean value theorem, which connects average speeds to instantaneous speeds. In real life, it guarantees that if a moving object starts and stops at the same place, its velocity was exactly 0 when it turned around. It is also heavily used in computer algorithms to find stable solutions. Let us wrap up what we have learned today. Rolle's theorem is essentially a formal mathematical guarantee of common sense. It states that any smooth, continuous path that begins and ends at the exact same height must have at least one point where it is perfectly flat. By carefully checking for continuity, differentiability, and equal endpoints, we can confidently locate the peaks and valleys of any mathematical model. You have now mastered a simple but profound rule that bridges the gap between basic geometry and the powerful predictive tools of advanced calculus. Great job!